In the 5th century BC, the famous Chinese military strategist Sun Tzu wrote The Art of War. In his chapter 10, the effect of the terrain of the battlefield on the outcome of war is analyzed. One way of defeating an enemy is to have barriers in place that prevent their advance. Our skin is an exceptional barrier that provides a first line of defense, impenetrable to most pathogens. Skin is the outermost surface of our body made of two major layers, dermis, and above it, epidermis. Epi in Latin means upon. The epidermis contains multiple layers of special skin cells called keratinocytes that produce a tough, fibrous protein called keratin. In the epidermal bottommost layer, the keratinocytes actively divide and multiply. However, with each cell division, the new layers push the former ones upward, that ultimately become dead skin. Let me explain. As the cells rise to the uppermost layers of the skin surface, they accumulate more and more keratin, but lose their nuclei and internal structures, forming a thick layer of keratin-rich dead cells. This layer, tightly packed cells, is very dry and water-resistant. The layers of the epidermis present a harsh, tough, mechanical barrier that protects our internal organs from pathogens trying to invade our bodies. The epidermis itself has no blood vessels, and thus is totally dependent on the nourishment from the underlying layer, the dermis. The dermis is made up of various cells, such as fibroblasts, and also contains hair follicles, sweat glands, sebaceous glands, as well as blood and lymphatic vessels. The interstitial space between the cells is rich with structural proteins such as collagen and elastin. These give strength and elasticity to our skin. Together, the dermis and epidermis create a formidable mechanical barrier that effectively keeps pathogens from entering our body. However, as mentioned earlier, the internal surfaces that line our digestive and respiratory and urogenital tracts are directly exposed to the environment as well, and so are potentially threatened by dangerous pathogens. The surfaces coating these linings of our tracts are more sophisticated, being able to selectively exchange and communicate with the outside world. Thus, we take in oxygen from the air we breathe and exhale CO2. We absorb nutrients from the foods we eat, and so forth. The cells that line our internal surfaces are mainly cells called epithelial cells, which are tightly connected to one another. In addition, these internal linings have special cells that secrete mucus, a rich, protein, viscous, protective fluid. Mucus is very important and coats the linings of our internal surfaces. Hence, these layers are sometimes collectively referred to as the mucosa. Mucus is slippery, thick, and sticky, and serves to entrap pathogens we inhale or take in when we eat. Like flypaper, bacteria or viruses get stuck and can't further penetrate and gain access to our internal organs. Thus, we are protected in the mucosa. We get rid of these pathogens when we cough, sneeze, or blow our nose. We also routinely swallow mucus-entrapped pathogens and thus dispose of them in our stomachs. Now, you all know that our stomachs are filled with very acidic gastric juices, which kill whatever pathogens we may have swallowed. The mucus also protects the epithelial lining of the stomach itself against the extreme acidity of the gastric juices. Moreover, mucus lubricates the intestinal surfaces, aiding the flow of food through the digestive tract. Now, whereas skin and the mucosa provide a mechanical barrier, they are also fortified by protective chemicals like oils, fatty acids, and most notable, lysozyme, an enzyme secreted in tears, mucus, and sweat. Now, surprisingly, the discovery of lysozyme led to events that literally changed the history of medicine. It was during World War I when Captain Alexander Fleming an army medic, saw more soldiers die from bacterial infections than of their actual battle wounds. After the war, Fleming set out to discover antiseptics, substances that would selectively kill bacteria and prevent death from infection. In 1923, his efforts paid off. He discovered the bacteria-killing enzyme lysozyme. Fleming's success was based on his developing techniques that revealed the bacterial-killing activity of the substances he tested. When suspect agents were applied to continuous bacterial cultures, bacterial lawns, on agar petri dishes, bald spots would appear indicating the bacteria were being killed. Indeed, killed bacteria by lysozyme could be seen as such bald spots or halos, indicating the absence of growth. In September 1928, Fleming had just returned to his lab after a summer vacation. There he found a stack of petri dishes containing old bacterial cultures he had forgotten and left unattended on his bench. One of the cultures was fortuitously contaminated with a fungus. Fleming noticed that around the fungus there was a familiar bald halo, telling of bacterial killing. Only the prepared mind of Alexander Fleming, gaining from his discovery of lysozyme, could have noticed and, more importantly, understood what he actually saw. Fleming went on to identify the killing substance secreted by the fungus, called penicillium, and named the new antiseptic penicillin, the first antibiotic ever. In 1945, Fleming, Chain, and Florey received the Nobel Prize in Medicine in recognition of their discovery and subsequent work on penicillin. So, skin and the mucosa provide a critical component of the innate immune system. What happens, however, when this first line of defense is breached?